It gives me great pleasure to introduce Dr. Michael Albrow, Scientist Emeritus of Fermilab, the Fermi National Accelerator Laboratory. Michael spent 18 years based at CERN in Geneva, Switzerland, doing experiments in particle physics. He was a CERN staff member, senior scientist at the Rutherford Laboratory in the UK, and a professor at Stockholm University. He began working at Fermilab in 1991, contributing to the discoveries of the top quark, the most massive known fundamental particle, and the Higgs boson at CERN's Large Hadron Collider. He became Scientist Emeritus in 2016 and continues to do research at Fermilab and CERN while writing and talking passionately about science. Dr. Michael Albrow.
Thank you so much. And thank you for the introduction and for allowing me to be part of this exciting event about exoplanets. And I'm going to start off by talking about how we know that there are, in fact, billions and billions of planets in our own Milky Way galaxy from a science point of view. So here you see an artist's impression of star rise on another planet called TRAPPIST-1d, which is the third planet from a red dwarf star. There are red giant stars as well. Stars come in all sizes and colors. As far as we know, this is a sort of realistic picture, but of course, we've never yet had such a view. All these scenes you see of planets, of other stars are, of course, artist impressions, but based on the scientific knowledge that we have about them. If you go to the website that I show you at the top of this, you can actually sort of move around your view and see a 360 view of this planet. The variety of planets is enormous, even in our own solar system. Imagine you're standing on one of these planets and you see your sun may be very big and red, or it may be very small and bright blue. There may even be two in the sky. You may feel twice as heavy, so you can hardly jump at all, or very light and leap far, but not as far as our astronauts could on the moon 50 years ago when the last ones were there. You may be able to breathe the air, or you may have to bring your own air with you. Most exoplanets are much too hot or cold for you to be standing comfortably, but billions in our galaxy alone are probably just right, what we call Goldilocks planets. We've now discovered so many exoplanets that surely nearly all stars have some, but we can only detect a small fraction around even the closer, brighter stars. And most of them have been found in one of two ways, called transits or wobbles. Here you see the number of planets that have been found over since the first ones were discovered around 1999. And in green, you see the number that have been found by transit method, where the planet goes in front of the star, and in red by what are called the wobble method, where we observe the star wobbling back and forth as it's pulled by the planets. Of course, if you guess that only 1% of these planets around other stars, and there may be 100,000 million of them in the Milky Way, as we think most stars do have planets. If you guess that only 1% of them are temperate, which may be an underestimate, like Earth, that allows liquid water and possibly life, that still means that you have something like 1 billion planets in this so-called Goldilocks zone that are not too hot and not too cold. Of course, so far we only know one that actually has life, that's ours, but it could be the only one, we just don't know. It depends on the probability that life actually gets started on a Goldilocks type planet. But if we are not unique, the chances are that there are millions and millions of planets with life in our galaxy alone. And of course, there are billions of other galaxies that are similar to ours in the visible universe. But once upon a time, the world was the only one that we knew. The dome of the heavens was, we didn't know what the stars were. They may have been just considered holes in the dark dome through which the light of heaven shone. And the Milky Way was just that, a milky mist. And the fixed stars were made patterns like Leo the lion, Capricorn, the goat. But there were some wanderers that did not stay fixed, associated with the gods like Mercury, Venus, the Roman goddess of beauty and love, Mars, Jupiter, and Saturn, and then the sun and moon, of course. They were different, special gods. Now, the motions of these planets were studied. Their complicated motions were measured. And this was the solar system, the one and only one that we knew under the starry firmament. But on rare occasions, a new star would appear for a few weeks, or a comet came to portend some disasters. Galileo was the first to look through a telescope at the night sky, and he saw that the Milky Way was in fact thousands of stars, too faint to see with the naked eye, and that Jupiter is a world with moons orbiting it. Venus is another world, sometimes showing a crescent like the moon. He saw dark spots on the sun, showing it was not perfect after all. Here is the sun showing some sunspots that come and go, and the sun rotates once every about 25 days at the equator, but it takes longer near the poles. It's not a solid body, and the sunspots move across. And I'll mention that later because it makes a little difficulty seeing transits of planets in front of the sun. So Galileo believed the view of Copernicus that the Earth orbits the sun, not the other way around. He got in serious trouble with the church and ended his life age 77 in house arrest. Giordano Bruno was not so lucky. He was older than Galileo. He was 16 years older than Galileo. He was burned at the stake. But Bruno was the first, as far as we know, to think that stars were like suns, only just too faint and too far away to be seen as other than the points of light at night. And that they probably have planets too. It took 400 years to prove that he was actually right. Here is a sunspot, a beautiful picture close up. There's art in the sky too, from a solar telescope in Hawaii. This is so huge, the Earth would actually fit comfortably inside that sunspot. And then we discovered, of course, more planets in the solar system. This shows planets in the solar system with the sun on the left, and the relative sizes are shown, but of course not their distances. The distances are shown in the graph underneath, and you see the distance along the left axis, the horizontal axis, and you see how close Mercury, Venus, Earth, and Mars are compared to Jupiter, farther out, and Saturn, 10 astronomical units, an astronomical unit being about the distance of the Earth from the sun, and then Uranus and Neptune further out. And the Voyager spacecraft are even way further out. Pluto is shown as a long band because it's not in a circular orbit, elliptical, and it comes closer and further away as it goes around the sun. And there are lots more things in the solar system. Dwarf planets, some of them are shown down on the right there, minor planets, moons, comets, and so on. Uranus, as seen by the Hubble telescope, and it has a ring around it. And this was discovered by Herschel in 1781, the first new planet to be discovered. Others before him had seen it, but not really recognized it as a planet. And it has its own moons. The right shows how it looks and the size relative to the Earth. On the left picture, the bigger one has got enhanced colors. Then the motion of Uranus was not right, according to the calculations of Newton's laws of gravity and Kepler's laws of planetary motions. It seemed to have been pulled forward and pulled backward. Hypothesized that that would be another planet outside Uranus, and it was calculated by astronomers where it might be in the sky, and was found just where it was predicted to be. It was Neptune. This was a planet that was discovered by gravitational pulls on another world, and it's the same method that we're using to discover planets around other stars, but by the pull of them on the suns. We've now landed on two other planets in our solar system, as you know, Venus and Mars. The picture at the top shows the landscape of Venus as shown by a Russian lander, Venera 13, way back in 1982. Venus is very hot and difficult to survive. In fact, that camera survived a couple of hours, and the picture at the bottom is a reconstruction of what it would have seen had it been able to look clearly out to the horizon of Venus, a very hot and dead world, of course. Have you ever seen a total eclipse of the sun? This is a picture of the one that happened in 2017. It was a very exciting thing to see. It crossed the United States, and I remember it, my first total eclipse of the sun very well. If you look carefully at this picture, you see it's of course something of a coincidence that the moon and the sun appear to be exactly the same size in the sky. So the moon just covers the sun, and you see the beautiful corona of extremely hot plasma that is around the sun. If you look carefully at the dark side of the moon here, you can see just some of the dark mare or seas that are what you see on a full moon, making the man in the moon. And how do you see them on the dark side of the moon, which is the night side? Imagine you were standing on the moon, on the dark side, during an eclipse. You'd see the full Earth in the sky, and you'd see the shadow of the moon as a dark spot moving across the Earth. The Earth would be bright in your night sky, and it's by Earthlight that we're seeing here the Mare on the moon. In the total eclipse of the sun, of course, the moon goes in front of the sun, and sometimes the planets that are closer into the sun, Mercury and Venus, pass in front of it. The first time a transit of the sun by Mercury was seen was by Gassendi back in whenever, and but it's very hard to see that. But Venus is easier to see with an eclipse of the sun when it's in a transit of the sun, because it dims the light somewhat more, but because it's a bigger planet and it's also closer to us. But it's only about 0.003% that the light is dimmed. If you didn't see that through a telescope, I mean, never look at the sun except through a special equipped solar telescope, but the light of the sun would dim by a small amount, about 0.003%, as the planet Venus moves across it. So you could, in fact, in principle, detect the loss of light of the sun by Venus transiting across it, even if you didn't have the resolution to see Venus itself. But that's a difficult thing to do on Earth, partly because of the atmosphere, but also because there are these sunspots on the sun. But this method, because it's the ratio of the sun area that you see in the transit to when it's not being transited, this method works for stars that are really at any distance away, as long as they're bright enough and the planet is big enough to see it. As we move out of the solar system, here you see a very famous picture of the Earth. Can you just see it? If I point to it here, this is the Earth. Carl Sagan called it a pale blue dot. Our planet is a lonely speck in the great enveloping cosmic dark, he said. 20 years after we left the moon for the last time, exoplanetary research has started in earnest with missions by space telescopes, starting with the Hubble in 1990, that is actually still operational, and then a series called the Spitzer telescope, which was operating until last year, Kepler, which was really very prolific in discovering enormous number of planets by transiting method, and the other tests, and the James Webb Space Telescope up on the top right here, which is scheduled for launch towards the end of this year, hopefully, and then future missions. You see them there. Now, the first planet that was discovered around another star, another normal star, not a pulsar, was this one called Dimidium. This is, of course, an impression, a sun-like star. That is a picture of the sun, actually, and this is an artist's impression of what the planet would be like compared with the size of the sun. It was called Bellerophon. I'm not quite sure what that means, but this was actually discovered by the radial velocity method, which is a method just observing the wobbles of the star towards and away from us, and I'll get back to that. The next planet discovered, the first one by the transit method, where the planet moves in front of the star and blocks its light a little bit, as you see by this little sketch on the right, where a planet orbits, moves in front of the star and dims the light by a little bit. This one was in 1999 by Hubble. It's called a hot Jupiter. Hot because it is very close to the star, and we can tell that it must be extremely hot. Jupiter, we call that because it's a very big planet. In this case, the light, it's so big that the light is dimmed by 15%. It's close into the star as well. But we can see by studying the gases around this star that hydrogen is being blown off by the heat of the star, about 10,000 tons per second being blown off. And then we've detected also heavy elements by a spectroscope, which I'll say a little bit more about in the future, with also some carbon and oxygen. So here is the picture of the Kepler Space Telescope. Of course, it's a photograph, but superimposed on the sky. And it has a digital camera with about nearly 100 million pixels. So it's a very big digital camera. And it's staring at one area of the sky, not very big, but covering 150,000 stars. It's pointed in a direction that is away from the center of the galaxy, because the stars may be so densely packed that planets are maybe less likely. We don't know about that. And of course, if you pointed it towards the completely opposite direction, that you'd have fewer stars in your field of view. The Kepler Space Telescope is able to observe something like 150,000 stars and look at their light 24/7 because it's pointing away from the sun and away from the Earth and looking for variations in their brightness. So this next slide shows an example of the first rocky planet that was discovered. You see on the right how a little sketch of how, as it moves in front of the star, the light dims by a little tiny bit. In fact, you see it's much less than 0.01%, about 0.01%, in fact, dimming. We have very sensitive light measuring. And when you see something like that happens, you think it's probably caused by a planet moving in front of the star, but you best wait and see it coming back again, and preferably another time, to get the orbit and be sure that it really is a planet moving across and not some thing like a star spot, like a sunspot or so. This planet is scorching hot. It's too hot for water, but it may still have oceans of molten lava and even rivers of molten lava. This is not much bigger than the Earth, but it's much, much hotter. Here is another impression of a planet, the first rocky planet that was found in the habitable zone. We call it the Goldilocks Zone. It's not too hot and not too cold, but at least just right to have liquid water on it, possibly. And this is called Kepler 186f. We number planets around stars by letters, starting with B, C, D, E. F means the fifth planet from the host star. And this is a very famous system called TRAPPIST-1. The first three planets here were discovered by Belgian astronomers, actually from ground-based telescopes, and they called it TRAPPIST because they celebrated by drinking their local beer, TRAPPIST beer. But since then, other the Spitzer Space Telescope and Hubble discovered more planets. And in fact, we know that there are about 7 planets around this star, and they're sort of shown in a sketch here. And the next slide here shows the light curves of these 7 planets. You see they're very well measured now. They're repeated because the period of these planets is quite short. They go around close to the star. So the top one there, a period of only 1.5 days. So we see it going across many, many times. Now, of course, we can only see these planets in transit when the orbital plane is in line with us. So we see them actually going in front of the planet each time and not above and below like Mercury and Venus usually do. These curves are all just displaced vertically to see them clearly on the same graph, but there are small dips in the brightness and they repeat again and again. The bottom one every some 14 days, Earth days, going in front of the star. It's an ultra cool red dwarf star, and this slide shows sketches of the relative sizes of the planets at the top, what they would look like. At the bottom, you see how their orbits compare with the inner solar system, much closer in because the star is small and the whole system is much smaller. And the star's cool a red dwarf star, but because the planets are much closer in, they can still have temperatures like on Earth. And we think that 3 of these planets are in the so-called Goldilocks Zone, which means that water could be there and possibly life could be there. And this next one shows an artist's impression of what you might see something like this if you were actually on TRAPPIST-1e, which is one of the 3 that they think could have water. This is water ice that you see here. And you see another planet in the sky transiting. They're close together, and so you can actually maybe see them as disks without needing a telescope. Now, the next slide shows another system, actually has 8 planets that we know of in this system. It's called Kepler 90. It was discovered by the Kepler Space Telescope. And the star is something like our sun, not like TRAPPIST-1, which is a red dwarf, cooler and smaller than the sun, but this is somewhat like our star. So they're all closer to the star than Earth is to the sun, and they're probably too hot for water or life. But there may be cooler planets further out we haven't seen yet because it's harder to find them as they're further away. The next slide just shows some artist impressions, but none of these have been imaged, of course, but they're based on the science we know about the sizes and the possible and the temperatures of the planets that we can calculate, because we know their distances and we know the temperature of the star itself. You may not have seen a total eclipse of the sun, but you've probably seen a total eclipse of the moon because they're much more frequent. And in this case, if you were standing on the moon, you'd see the Earth moving in front of the sun. It's a transit, if you like, but the Earth appears much bigger than the sun from the moon. And you see a reddish color, a very commonly reddish color. And that's because if you were standing on the moon, you'd see you could measure the Earth's atmosphere composition. Now, how that works is probably familiar to you, but I show in this slide Newton, who discovered that the sun's light could be broken up into colors by a prism. Of course, that is what a rainbow does. So he was able to do this with a glass prism. We now understand, of course, that the light is spread out because the different colors have different wavelengths. And at the bottom, you see a much more precise spectrum of sunlight than you can see with just a simple prism. This is based on a diffraction grating, the sort of thing you get with on a CD or DVD, if you look at the light scattered there. And here you see dark lines in the spectrum, which is where light of certain special wavelengths is absorbed. The D lines are due to sodium. Molecules have their own, or elements and molecules in the infrared have their own absorption lines, and you can measure them very precisely. At the top right, you see light emitted by the sun, and you see the two yellow bright D lines. Light is emitted at certain wavelengths and absorbed at certain wavelengths when it passes through. Now, by measuring these wavelengths very precisely, we can measure whether the star or sun is moving towards us or away from us because of this shift in wavelength, which is an analog of the sound shift you hear if, for example, you're standing by a car rushing past you and you go, eow, eow. So that's the so-called Doppler shift. And it's the same with light, only speeds have to be much bigger than that. But when an object moves away from you, the wavelength shifts to the red, and that's how we know the universe is expanding. When it's towards you, it shifts towards the blue. And we're able now very precisely to measure shifts of these dark lines in the spectrum of stars and measure the speed with which they are moving away or towards us. And this is now so precisely done that we can actually measure speeds not too many meters per second away and towards us. And now many planets have been observed because not only does the star pull on its planet, but the planet pulls back on the star. It's a mutual attraction sort of thing. And here's a system called Gliese 581. It's a red dwarf. And we found 5 planets around this system because of their pulls on the star, the wobbles to and fro. And of course, it's quite complicated because they've all got different periods around the star. And so they give a complicated pattern. And now this is being studied with a European Southern Observatory telescope in Chile, up high to get above much of the atmosphere, and it's called HARPS for High Accuracy Radio Velocity Planet Searcher on this telescope that you see on the picture on the right, with a very precise instrument that can measure small wobbles of these spectral lines. Here's some graph from this HARPS instrument, and at the top on the left, you see the radial velocity of the star, and the scale is very precise. Like on the top left, is from 0 to 5 meters per second. That's just a fast run as the star moves away from us and towards us. You see only measurements when this thing is observed in the night sky, so you're not seeing it 24/7. For that, you need to go into space. But when able to fold these together because and subtract 2 out of the 3 wobbles and see on the right, you see actually the movements of the star as it's pulled back and forth by the planet. And you see here 3 planets that have been observed this way. I circle, you see it's an international collaboration with Switzerland, France, Chile, and Germany, and so on. What about actually seeing the planets themselves? We're beginning to do this. And here's a picture showing the positions of 3 planets. They're not really as big as this. This is just blurred out by the pixels on the detector. But the star has been blocked out electronically after the image. And one has seen, in this case, 3 planets. They're big, bright, relatively bright planets, but the star was completely blacked out by a clever device called a vortex coronagraph. Now, there are missions planned to be able to observe planets around other stars from space. And one project is Star Shade, which is something that would be sent up into space, folded up, and then open up in space and positioned between the telescope and the star to cover just the star's image and allow it to be easier to see the planets in the orbit of the star. This next slide shows now that we are starting to be able to detect composition of atmosphere. In the bottom, you see this star called WASP 39b, and we've detected water vapor in the atmosphere of this as it transits in front of the star. This is something that is taking off and could be the way that in the future we will be able to detect the composition of planet atmospheres around stars to see whether they have been affected by life. So let me talk a little bit about this habitable zone. Here's a nice picture I like, credit Luke Forsyth, showing how there's a habitable zone around a bonfire. You don't want to get too close or too far away. And it's an analog to being not too close or too far away to a hot star where life could be, or at least liquid water could be. The transiting exoplanet survey satellite called TESS has found 3 planets, and one of them is just about in what we think of the habitable zone, knowing the distance of the planet and the temperature of the star and so on. Of course, it's not such a sharp zone. We find life in very unusual habitats on Earth, but probably to get started, it needed to be in a reasonable temperature, not too hot and not too cold. It's likely that the first evidence we may have that some other planets, exoplanets, do have life is from their atmosphere composition. Here I'm just showing some pictures. Mars has got an atmosphere, as you know, a hazy thin atmosphere. It's about 1% of the density of Earth's atmosphere. Jupiter's got a very turbulent atmosphere that is very deep. Titan has an atmosphere itself as the moon of Saturn, not a planet. And Plato even has an atmosphere, and here you see it backlit by the sun from the Voyager spacecraft. The closest exoplanet that we have found is around Proxima Centauri b. Proxima means close, and Centauri means it's in the constellation of Centaurus. It was discovered in 2016. It's only 4.2 light years away. The star is cool and red, and it's close in 11 days to take 11 days of our days to go around the star. But it could have liquid water, oceans even, and this is an artist's impression of it. Now, the Spitzer Space Telescope, which lasted for 17 years until last year, has been measuring spectra of molecules in a protoplanetary disk, not yet quite the atmosphere of a planet, but close, and seeing signs of carbon dioxide and acetylene and other complex molecules. So this is the direction in which we're going to try to detect molecules that are actually, or the composition of an atmosphere that, as we know in Earth's case, has been changed by life on Earth. And then in the future, well, the James Webb Space Telescope, we hope, will be launched later this year. It has huge mirrors that are actually sent up separately and assembled very precisely to form an extremely large mirror and study the infrared transmissions of atmospheres around other stars. This is an artist's concept of another beautiful picture of what might be like on a young planet around a cool star. And this is pictures from NASA. Now we have found thousands of planets around other stars. And of course, we can only see those by transit if their orbit happens to lie in the plane so that they move in front of the star. And wobbling of stars can be seen even if they don't go in front, but not if their orbit is like at 90 degrees to our view, because then the sun is pulled sideways and not in forwards and backwards. Now this graph shows on the vertical axis, you see the mass of the planets that we can measure by these methods, compared with the mass of the Earth, and 1 is the mass of the Earth. I put a line there. And the horizontal axis is the period or the year of the planet in Earth days. So the Earth is 365 days. I put a line there. So that red star I plonked on there, which is where the Earth would be. So we haven't yet found planets that have the mass of the Earth and the year of the Earth as far out. They're always more massive or closer in or both. But knowing that we can only detect a small fraction of the planets around other stars, and we can estimate that just probably every star, at least in this part of the galaxy, maybe not right in the center where stars are very dense, has planets. So there's probably something like as many planets in the galaxy as there are stars. That's 100,000 million. I like to say that rather than 100 billion. Our galaxy is one of many. As you know, you can look out the Andromeda galaxy, which you can see with the naked eye on a clear night. And then we found by staring into space with a long exposure, like the Hubble Ultra Deep Field. On the left, you see, if you can just see here, the area that the extra deep field studied, looked at this area of the sky where there are no stars in our galaxy in this view. That's compared with the size of the moon. And you gave an exposure for 12 days with this huge camera telescope. And this is a picture that came out, and every dot here, everything here is a galaxy. You can work out that there's something like 100,000 million galaxies in the visible universe, which is something like the number of stars in our own galaxy. So I've come to the end of my introduction here. This is a picture from NASA. Explore the galaxy and have fun doing it. Thank you very much.
I want to invite you all now to give a big round of applause to Michael Albrow. Although we are disconnected, I promise you he can still hear you. Thank you so much for connecting the history of science to our present day experience, discovering the shared universe of exoplanets that we all inhabit.